Hello all, welcome to this class on generative models. Last time we were formulating the generative models through a probabilistic framework. I covered the basics of probability theory, the broad philosophy of how to construct mathematical tooling around modeling uncertainty. In this class, I will continue those ideas and extend them to the definition of how to formulate the framework of generative modeling from a probabilistic viewpoint. A quick recap before we start. So last time we saw that in statistics we use the probability triplet, which is the sample space, the event space, and the probability measure to quantify the uncertainty that exists within a system that we are trying to model. And at the end of the last class, we also saw that typically we one would not have access to this particular triplet. Neither we'll have access to the sample space nor to event space or the probability measure. Therefore, for convenience, we define another function called the random variable that would map the sample space, the members of the sample space, to real numbers or real vectors. And then once that function is defined, the event space gets mapped to what is called as the sigma algebra, or the equivalent of the event space in the probability triplet is the sigma algebra here, and the probability measure gets translated to what is called as the probability distribution function. We also defined what a probability distribution function is. A probability distribution function is defined on the range space of the random variable x. So you take a vector or a scalar, which is the range space of random variable, and you can evaluate the probability distribution function at that particular at the member of the range space of the random variable. That is defined as the probability of an event. So please note that probability distribution function is a valid probability measure. It is equal to the probability measure, and this probability measure is the measure that we defined on top of the event space of the underlying sample space, right? Now, it is the probability measure of that particular event which gets mapped to this particular set, which is infinity to x, under the function called the random variable. So it's the probability measure of the inverse image of this particular subset of real numbers under the function called random variable is what is defined as the probability distribution function. So if you evaluate the probability distribution function at a particular point, what you are calculating is the probability of that particular event in the sample space, which gets mapped to this particular set under the random variable that we have defined. Okay. Now, as I at the end of the last class, I also told you that this triplet is not accessible, and therefore we define the random variable. And what is accessible to us as practitioners is this particular triplet, which is the real numbers, the Borel sigma algebra, and the probability distribution function. And we need to work with this because this is what we measure at the end of the day. We stopped the last class there, so we will continue from that discussion and then now and go on till formulating what is generative modeling and how does one formulate the problem and then use algorithms to solve it. Now, that's the broad narrative of this particular session. Okay. So one thing that is to be recalled is that we have in entire probability theory, we start with a sample space, an event space, and a probability measure. This is what we start with. We assume that nature is generating data in this framework, and then define a function called random variable. So I cannot stop emphasizing on the fact that random variable is a function. Okay, so because that's very important to have that particular worldview. Function x called the random variable that is defined on the sample space, and it is a d-dimensional real space in general. Okay, so x, a random variable, is a function that is defined from the sample space and it maps to a d-dimensional real space. A small note in my notation, I'll be writing RD multiple times in this course. So by RD, I mean a d-dimensional Euclidean space. So it's a d-dimensional, the members of this is a d-dimensional vector where d is any arbitrary positive integer. So if I write R3, then I'm talking about three-dimensional vectors. If I write R2, it's two-dimensional vectors. In general, if it's RD, it's a d-dimensional vector. Okay. So random variable is a function that takes the elements of a sample space and maps it to a d-dimensional real space. And what's important is in practice, right? So once this function is defined, once a random variable is defined, so we'll have the d-dimensional real space and the sigma algebra, the subsets of this RD, and the probability distribution function. This is what we will end up having, and we'll have to work with this. Yeah, we'll have to work with this. Now what I'll do is I will connect the discussions that we have so far, we had so far, to some of the practical problems, so that you will be able to appreciate what I'm saying much deeper. So let's consider the example of a problem with images as data space. Okay, so what is that we are dealing with? We are dealing with images. So what is an image? If you take an image and read it in a computer, you will have a grid-like topology where we'll have m number of pixels here and n number of pixels vertically, and each of the pixel or a grid here will have a value between, let's say, 0 to 255 or whatever, depending upon what the bit length is. Now this is what we will have, and we'll have multiple of them, let's say. So let's say that we have multiple images that we are dealing with. Now how do we fit in whatever we saw so far in this framework is the question. Okay, so now these are pixels. So they are simply values, some integers. So between, let's say, 0 to 255, it will just take one integer value between 0 to 255, and there are mn of them. Okay, now one way to look at this is that this can be visualized as a vector in R mn dimensional space. So what do I mean by that? Let's say that this m is, let's say it's 100, and you have n to be equal to 200. So you have an image that is of size 100 by 200. If that's what we have, then an image will be a point, okay, or it's a point or a vector in R 20,000 dimensional space. Now just like you know what a point is in a two-dimensional Euclidean space, right? If I write, let's say, 2, 3, then you go 2 units in one direction and 3 units in another direction, and this point is referred to as 2, 3. Imagine you have 20,000 axes in a Euclidean space, and now every image or every data point that we have in this particular framework will now become a point in a 20,000 dimensional Euclidean space. So this d here, whenever I write RD, right, this d is 20,000 now. Okay, now what we have with us are vectors that lie in some d-dimensional Euclidean space. So now an image is one vector in a 20,000 dimensional space, and a similar analogy can be drawn for different kinds of data types. For instance, if you are dealing with, let's say, textual tokens, so this is the example of an image. So now if you have so this is example A. So for example B, if you take tokens of text, tokens of natural language text, Oh, by the way, before I continue, uh, these 20,000 values, what are these 20,000 values? These 20,000 values are the ones that are filled in different pixels. So the way I'm imagining this is that I'll take the first row and then take the second row and concatenate with the first row, and then take the third row, fourth row, fifth row, and just concatenate and make it a very long vector of length 20,000 dimensions. Whatever values are there in the pixels of the image will now become the values or the entries of this 20,000 dimensional vector. So basically, the worldview that I want all of the students to have is that every data point that we deal with is a vector in a very high dimensional Euclidean space, and the dimensionality of that space depends upon the kind of data that you are dealing with. Okay, so let's take another example where you are looking at the tokens of natural language text. So you have a passage of text, let's say, which is a paragraph. So we can have each word is a vector in some RV dimensional space, where V is the length of a dictionary or a vocabulary. Now, what do I mean by that? Let's say that we have an exhaustive list of all possible words that can come up in a language. That is what a dictionary is. Now, what I'll do is I will represent each of the word that is appearing in my passage as a vector of ones and zeros, and this vector will have the value 1 in the position that corresponds to the position of that word's occurrence in the dictionary and 0 elsewhere. Okay, so in this sense, every word in the dictionary is represented as a vector of zeros and ones, and the length of that vector is equal to the number of words in the dictionary, right? So in this sense, a passage or every word in a given textual passage is now represented as a vector in a v dimensional space, where v is the length of the dictionary that we are considering. So the representation that I just talked of, which has all zeros but one at one particular place, which corresponds to the position of occurrence of the word in the dictionary, is called one hot representation. That's one of the multiple representations that one can think of. But the idea that I want to convey is that every word, so this token may be a word, it can be a syllable or anything. Let's, for the ease of understanding, let's consider them to be words. Each word or a token is a vector in a v dimensional space, and this vector is a one hot vector in the sense that it can be having all zeros but one where which corresponds to the position of occurrence of that particular word in the dictionary. So this is one other example. The third example is, let's say that we have a speech signal, an audio signal as data. So how do we represent this? So this there is a speech signal, okay, which is a one dimensional signal over time. So you have the voltage that we measure, okay, along the y-axis, and along the x-axis we have time. So this is one utterance. One of the use cases of this is that you want to generate speech, or you want to, given a text, you want to generate the corresponding speech, or you want to recognize speech, and so on. These are the kinds of applications that we see. Now, how do we represent this in machine learning? Is that now take this, okay, and chunk this into windows. So this is window 1, and this is window 2, and so on. Now each of these windows take all the values of the speech signal in this window, and now that becomes a vector in some. So each window is a vector in some R, let's say W dimensional space, okay, where W is the length of the window. Okay, so I can go on. So I can take multiple examples and show you how to represent each of the data types as a vector. But the summary is that, so the take home message or summary is that, so every data point by data point I mean an image or a speech window. It can be a word in a sentence, anything. So it depends upon it completely depends on the problem that we are trying to solve. every data point that we deal with is a vector in an RD dimensional Euclidean space. So this is the take home message. So whenever we talk about data in this course later, that okay, we have a data point that we are dealing with, so you should always imagine that we are talking about vectors in a d-dimensional space. This can be an image or a video chunk, or it can be a speech signal, it can be a word or a token or anything. It can be a piece of code, for that matter. It can be anything. Now, in further in this course, we will deal with all the generative algorithms in a data set agnostic manner or data type agnostic manner, in the sense that the algorithms that we see are not different for different kinds of data sets. Whenever there are some nuances that are specific to a particular data type, I would mention that. But in general, the algorithms that we discuss in this course are data set agnostic, data type agnostic, that in that they can be applied to speech signals, they can be applied to vectors, or rather natural language tokens, they can be applied to code, they can be applied to speech signal, or any kind of data type. Okay, but yeah, so the summary is that we have to consider each of the data point that we look at as a vector in a d-dimensional Euclidean space. Okay, now how is this all relevant to whatever we were seeing in terms of probability theory is as follows. Now suppose we have a random variable, that maps the sample space to RD. Okay, so this is the random variable X that we talk of, which maps the sample space to a d-dimensional real number, d-dimensional Euclidean space. Then the data points that we would have, the data points that are vectors in RD, now under this worldview are the members of range space of the function random variable. So this is what the relevance is. Right? What do I mean by this? Now suppose we have an image, and we already know that an image is a vector in RD. Now this vector should be looked into as the member of the range space of this function called random variables. Okay, whenever we define a function, we have a domain and a range, correct? A function is a mapping from two sets. One is called the domain and the other is called the range. So the range set of a random variable is what we should consider when we are looking at data points. So every data point that we encounter is a member of the range space of the random variable. Or in other words, the moment we see a vector in RD in the probabilistic worldview, we should always look into that as a member of the range space of a function called random variable, which in turn means that there exists an underlying sample space which has been mapped to this particular vector under a function called random variable. So that's the worldview that I want all of you to have. See, for in the probabilistic machine learning, every vector that we see, every data point that we see is a vector in RD. However, that vector is a member of the range space of a function called random variable, which in turn automatically tells you that whenever there is a random variable, there is an underlying sample space, and whenever there is an underlying sample space, there is always a probability measure that has been implicitly defined on that sample space. Okay, so all the data points or data set that we see are vectors in RD, and these vectors, this RD now is the range space of a function called the random variable, which implies that there exists an underlying sample space that we don't have access to. Okay, now this completes the story. As I told you that we will not have access to the sample space, the event space, and the probability measure, right? We don't get to see that at all. The beauty of this is that the moment we define a random variable implicitly, of course, we don't even have to know what the underlying sample space is, because this random variable as a function has taken the burden of mapping, or rather converting all the abstract elements of the sample space to something that we can measure in RD. Okay, when we take a sensor like an image sensor, which is a camera, or a speech sensor such as a microphone, what we are actually doing is that we are measuring or we are converting the members of the sample space into something that we measure in RD. That's the implicit, that can be viewed as what a random variable is doing. And once we measure it, while we work with the members of the elements of range space of the random variable, the implicit understanding is that there always exists an underlying sample space that is giving rise to this particular measurement in the under the random variable as a function, and there has been a probability measure that has been defined on the underlying sample space. Okay, so the idea is that the once we measure, so we'll have the elements of RD, and we consider the sigma algebra, which is a subset of RD, and a probability distribution function that is a surrogate for the probability measure. Okay, so this is one part of the story. The other part is there's a climb. See, remember what our fundamental goal was. Our fundamental goal was to model the uncertainty in the system that we are dealing with, correct? So the system can be the outcome of a coin toss, or it can be the outcome of a roll of a die, or if you want to make it practical, it can be the outcome of generating a natural language. That is what the large language models are doing. They are generating natural language. It's the system that they are trying to model is the system of human language. Okay, so now whatever system that we are dealing with, the idea was to deal with the uncertainty, and we said that the statistics or probability theory will give you a mathematical tooling to accomplish that task. Now let's come back to that. Now, what is the mathematical tooling that we have? We have defined what the probability measure is, and we have defined what the sample space is, and we have defined what a probability measure is. And of course, then because of the practical measurement issues, we said we'll not work with the sample space, the event space, and the measure, but we work with the d-dimensional Euclidean space and the Borel sets and the probability distribution function. All this is fine, but how far are we in tackling our original question of modeling the uncertainty in a system is the point. Now here is a claim that I make. The probability measure that we defined on the sample space, right, which was denoted by script P, completely specifies the underlying sample space. So this is the claim that I'm making. So what is the idea? The moment we know what the probability measure is, suppose we know everything. Probability measure is a mathematically it's a function again, right? It takes from the elements of the event space and maps it to close 0, 1. That is what we saw. Now suppose I know the probability measure, the function that I have defined on the sample space, then I can guarantee that everything that I want to do regarding quantifying the uncertainty in the system is known. Okay, why is that? Intuitively, the idea is the following. See, why do we even what's our fundamental goal? Our fundamental goal is to quantify the uncertainty in the system, I told you. Now, how do you quantify that? The very probability measure that we have defined is the function that quantifies the uncertainty in the underlying system. So if I'm interested, let's take the example of tossing a coin, and the system that I'm trying to model is this process of tossing the coin and observing what the outcome is. Now, if I have to answer questions like, what is the likelihood or what is the uncertainty associated with 10 tosses turning head, or the 5th toss turning tail, or 6 tosses turning head and the 7th toss turning tail, and so on. If I know what the underlying probability measure is, which is the function that assigns values between 0 and 1 with the certain properties that we looked at, right, to every member of the sample space, then I can answer all of those questions, okay, that would quantify the uncertainty of the system completely. So that's what it means. Okay. Now, if this statement is true, then the goal of entire engineering exercise around uncertainty measurement will be towards estimating or evaluating or understanding what the underlying probability measure is, because that's the only thing that we would like to know, right? So now the goal of machine learning, or rather any statistical measures, is to estimate the probability measure, the underlying probability measure. Underlying probability measure. So this is the central question of machine learning. So be it the discriminative models or the generative models, the formative question that all model building, all algorithms that you see, from neural networks to kernel machines to linear models to generative models, the underlying the fundamental question that all of the machine learning is trying to answer is this, which is we are interested in estimating the probability measure. Now, I told you that in practice we will almost never have access to the sample space. What do we work with? We don't work with the sample space and the probability measure. Rather, we work with the random variables, or not even random variables. We work with the elements of the range space of the random variables, which is our RD, which are our data points, and the probability distribution function. And I also told you that probability distribution function completely specifies the probability measure as well, because the kind of sets that we are considering while we define the probability distribution functions are such that if you estimate the probability of such events that we have defined while we are defining the probability distribution function, then we can obtain the probability measure associated with any of the member of the sample space, is what we saw, correct? Therefore, in practice, this particular question, okay, under the above question, translates to the following in practice. The above question translates to the following in practice. What is that? What does that translate to? So it translates to, so now it becomes, so practical goal that estimate the probability distribution function. Estimate the probability distribution function. See, note how this got translated from estimating the probability measure to estimating the probability distribution function. Why? Because we will not work with, see, I told you, right, this is the triplet that we are working with, not the omega fp. We are working with rdbpx. Therefore, if we have elements of rd, the question is estimate px, not p. And I told you that estimating px is equivalent to estimating p, because the probability distribution function is defined that in that particular way. Okay. Now this is the central question of machine learning, that we need to estimate the probability distribution function. Okay. All machine learning is this, estimating the probability unknown probability distribution function. Now, any estimation problem will beg some data, in the sense that it will beg some input, right? I mean, you cannot say that, oh, estimate a probability distribution function. The question that we are asking is, what is the underlying sample space that we are dealing with, and what is the wherewithal that we have to actually solve this problem, correct? Now, let's look at that. The inputs that are provided for an ML problem. So in general, what are the inputs that we are given with? So we are given multiple data points. So this is our starting point. I mean, you might have heard this colloquial saying that data is the new oil, right? So it's the raw material. So just like the crude oil is the raw material for most of the non-renewable energy that we consume today, data is the oil, as they say, the raw material for all machine learning that we do. So in our framework that we saw so far, what is this data set that we are talking about? We are given multiple data points. Let's call them x1, x2, up to xn. So we are given all this. So what are these? Each of xi is an element of rd. Okay, examples of this can be, so we are given n set of, rather n set of images. It can be n pictures, that can be our data set, or you can they are n paragraphs, so, or n code snippets. It can be anything. So what is the starting point for all machine learning is that we are given n data points which are elements of RD. So think of it like having n number of vectors in d-dimensional space. So I've already told you what does it mean to visualize an image as a data point in RD, right? It's a long vector that we are talking about in some high dimensional space, and we are given n of them. So suppose, if you are familiar with machine learning earlier, then you start with a data set, right? A data set will be, say, 1,000 images, 10,000 images. All of them are these xis here, and all of them are data points in some d-dimensional space. Correct? Now, how does this connect to the discussion that we have so far? Is that, so now all of these xi, so let's give this set a name. Let's call this the data set. Okay, we have a set of n vectors in RD. Now in the probabilistic framework, so each of these xi, okay, is a member of RD that we anyway know, right? I mean, because they are vectors in RD. Now this is, so this RD is, which is the range space of a random variable, a function random variable x. So what are we saying here? We are saying that, look, in the probabilistic framework of dealing things, the moment you see n images, you should always think of them as n data points in d-dimensional real space. And how did we get these n data points? We got these n data points by operating this function called random variable on the elements of a range space, a sample space. So we had an underlying sample space omega, and this function called random variable operated on this and gave us elements in RD, and that is what we are observing as data set. This is very, very critical to have this mindset, because going further in the course, I will not be repeating this. I'll only be saying that, oh, we have n data points. Whenever I say that we have n data points, you'll have to visualize them as members of a d-dimensional real space. And this d-dimensional real space we got from operating a function called random variable on the non-measurable or unobserved underlying sample space. So this is the worldview. Now, which implies, so this implies that there exists a sample space omega and the corresponding probability measure p. We have a corresponding probability measure p. So this is an implicit assumption that we are making in all probabilistic machine learning. The moment we see some data, we are making this implicit assumption that this data set that I am seeing are actually the members of the range space of the function called random variable that operated on the sample space. And because it operated on a sample space, there exists a probability measure p that we don't know. Okay, and since there is a random variable that we are talking, a probability measure p and a distribution function px. Distribution function px. So this is denoted this way. So we have n data points I equal to 1 through n, okay, that are sampled from an underlying probability distribution function px. So I will be using this notation multiple times in this course. This is the shorthand to convey these many sentences. Okay, the starting point for all the algorithms that we'll be seeing so far will be this, that I'll tell you that assume, or rather given that we have n data points, that are this tilde denotes sampled from. Okay, now I'm saying that I have n data points that are sampled from an underlying probability distribution function. What do I mean by that? The meaning of this particular equation is that, look, I have n data points, which can be n images, n vectors, or n code, n speech, anything, and all of these are members of some d-dimensional space. To continue, I will write this as all xi's are actually in Rd. Right? This is what I'll write. So all of these are members of Rd, and this Rd is the range space of a function called random variable x. And what did this function operate on? This function operated on a sample space omega, and there exists an underlying probability measure that got translated into a function called probability distribution function. Okay, so now remember that all our discussion started with this thing called a random experiment, right? There is an experiment that is going on, and the outcome of that experiment is what is enumerated in the set called sample space, right? Now, all I'm saying is that how did we get these n data points, by the way? We got these n data points by repeating the underlying random experiment n number of times. Okay, now it's like this. Suppose the underlying random experiment is like tossing a coin. We got n coin tosses, or n outcomes of the experiment called coin tossing, and we have enumerated all of that in a set called D. So somebody tossed the coin for n times. Now if the underlying random experiment is that of generating or taking images of sceneries, or rather generating natural language text or something, then that random experiment is being repeated n number of times, and every time the outcome of that is getting translated into a vector in d-dimensional space with the function called random variable. And because there exists a random experiment and a sample space, somebody has defined a probability measure, underlying probability measure, that gets translated to what is called as a probability distribution function under the function called random variable. So this is the story. Okay, so now from now on I will not repeat this. I'll just say that given D, which is a set of data points that I have defined above. So given D, so estimate the unknown probability distribution function. So now this becomes the central problem of the entire machine learning. So starting from linear models, linear regressions, to the Bayesian models, to neural networks and LLMs, and all the generative modeling, the one underlying sacrosanct problem that we will be solving is that of estimating the distribution function given data. Now what is this data? I'll repeat it again. Data points are the outcomes of n repetitions of the underlying random experiment, and whenever there is a random experiment, because we are measuring, there is a function called random variable that has transformed the outcomes of that random experiment into vectors in Rd. Okay, so this is the central question of machine learning, which is given data set, we want to estimate the underlying distribution function px. And note that px is completely unknown. So why do we want to estimate px? We want to estimate px because we want to model the uncertainty associated with the system. And I already told you that the moment we have what px is, then we can answer many questions that arise about quantifying the uncertainty of the underlying system. So that is the fundamental question that we are trying to answer here. Okay, now with this, let us see what is the general recipe of how does one go about solving this problem. Okay, so now given that we have formulated it, we will see how to estimate this this underlying what is the general recipe or algorithmic way to estimate this underlying distribution function given realizations. Okay, by the way, these are also called the realizations of the random variable. Different people use different terminologies. So what do you mean by realizations of random variables? Again, as I said, random experiment is being conducted n times, and each of the outcome is getting translated into a vector in d-dimensional the vectors in d dimensions using this function called random variable. That's what is called as realization of random variables as well. Okay, so now we'll see the general algorithmic recipe of how to solve this particular problem of estimating the underlying distribution function. Whenever I say distribution function, I mean the probability distribution function. For brevity, I will just use the word distribution function. So the question is of estimating the underlying distribution function given the data set D, which are n realizations of the underlying random variable. Now with the previous lectures, you should be able to appreciate this particular sentence statement that I'm making, that the central problem in machine learning is to estimate the underlying distribution function given that we have n observations from the random variable. Okay, so this is the statement that you would see in almost all the machine learning textbooks and the research papers, that the central problem in ML is to estimate the underlying distribution. Now we talk about generative models, right? Generative modeling. In generative modeling, we will add a small corollary to this particular problem, that once we estimate in generative models, the problem does not stop at problem is to not only estimate px, underlying probability distribution function, but also learn to sample from it. Okay, so now I introduced another terminology which is sampling from an underlying distribution function. So what do I mean by this? So sampling is the process of conducting the experiment or the random experiment that gave rise to the sample space omega. So what is this? Now we started the entire discussion by saying that that there is a random experiment that is happening, right? I mean, tossing a coin, rolling a die, generating an image, or rather taking a picture. All these are random experiments, right? So there's this idea called sampling, where we would come up with algorithms that would simulate that would simulate the underlying random experiment that is giving rise to the sample space. For instance, can you suppose we are looking at the random experiment as tossing a coin? The question that we are asking is, can we simulate a coin toss synthetically? Okay, if we are rolling a die, then the question that we are asking is, can we simulate the roll of a die that actually gave rise to this particular data set? Or if we get to the practical world, then the question that we are asking is, can I create new images that does not exist, right? That's what your image generation is all about. Can I generate human-like text? So that is what these LLMs are doing. They are generating human-like text. Can I generate human-like code? Okay, that is your the code LLMs that we look at. Now, the central underlying problem that all of these are trying to do is, we need to learn how to sample. Okay, what do you mean by sampling? Sampling is the process of conducting or having the ability to conduct the experiment that gave rise to the sample space omega without having access to the real omega at all. Okay, now this is generative modeling. So in generative modeling, we are not only interested in estimating the underlying probability distribution function. In fact, roughly speaking, in discriminative models, we end at this problem where we stop at estimating the underlying distribution function, because the questions that we are interested there is of that particular nature, where we want to know whether let's say we are solving the problem of a classification, right? Given an X-ray, we want to know whether this X-ray is diseased or not. So that's the question of estimating the underlying distribution function and stopping at it. But in generative models, we will not stop at estimating the underlying distribution function. We will also ask one other uh, question on top of it, where we will say that we given data set, okay, which are samples that are drawn from the underlying distribution, we want to estimate the distribution and also learn how to sample from it, which is simulate the underlying experiment that gave rise to the sample space. Okay, now more concretely, the central question in generative modeling, therefore, let's formulate with all the tooling that we have. So problem formulation for generative AI. This term Gen AI is a sort of cliche, right? I mean, it's just models that can sample, but anyway, we will use the terminology that is used in practice. Now we are given a data set, D. So what is this data set? Let me write it in a different line. So given a data set D, which is a set of n samples. So these are all sampled in accordance with a particular underlying probability distribution function, and this distribution function is unknown. So we have n realizations of the underlying random variable, and each of these xi's are members of a d-dimensional Euclidean space. So given this, the objective of Gen AI is to use this data and estimate px, the underlying distribution function, and sample from it. That's it. Okay, so this is the question that we'll be answering in multiple ways in this particular course. Okay, so this is the problem setting that we have, that we are given n data points which are n realizations of a random variable. Given that, we want to estimate the underlying distribution function and also learn to sample from it. So I've defined what do you mean by why do we want to. I've told you why do we want to estimate the underlying distribution function, and also sampling is obviously we would like to simulate the random experiment. Now one might ask this question, right? Can't we just learn to sample from the underlying distribution without estimating the distribution completely? It turns out no. One should know how to estimate the underlying distribution to learn to sample from it. And we'll see many instances of this throughout this course, that the central problem is distribution estimation. So even for generative modeling, the model has to either implicitly estimate the distribution or explicitly estimate the distribution before it learns how to sample from it. Okay, so the foundational question that we will be tackling in this entire course is this: that we start with n realization of a random variable with an unknown underlying distribution, and all these are data points in RD. Given this, the question or the problem that we will be solving using variety of algorithms. So your diffusion models and VAEs and adversarial models, LLMs, autoregressive models, state space models, all of them are trying to answer this one particular question, that given n realizations of an unknown random variable with an unknown distribution, or rather a random variable with an unknown distribution, you estimate the underlying distribution either implicitly or explicitly and learn to sample from it. Okay, this is the central question that we would answer in the entire course of generative modeling. Okay, so before I conclude this particular session, let me just give you a broad recipe or a high level description of how all the models that we will see further in this course are equipped to solve this particular problem. So let us look at the general recipe, let's say framework for solving the above problem. So what is the general framework that is there to solve this problem? Okay, so this is what we do. Any engineering problem, right? Any modeling problem that we would want to solve. So how do we solve? In general, you have been looking at this since your high school. Suppose you are given a few points in Euclidean space, and somebody would ask you to connect the dots, or rather fit a curve for this. How do you do? The first thing that anybody would do is by assuming that all the points actually come from a particular shape. You assume that it's a line, or it's a quadratic curve, or a cubic polynomial or something. And once you assume that, you would try to estimate the parameters of it. That's what curve fitting is all about, isn't it? So assume that my points are coming from a line, and estimate its slope and intercept, because a line has two parameters. Now assume that it's a circle, estimate its center and the radius. Assume that it's a conic section, and estimate its parameters, and so on. So this is the general principle that is applied for the problem of generative modeling as well. That we start by assuming that the underlying unknown distribution function that I am trying to estimate uh, actually has a particular parametric form. Okay, and we estimate the parameters of that particular function uh, that we have assumed on the model. So this is the general framework. Let us make that idea concrete. So let's start. The first step is to assume a parametric form on the unknown distribution function. Okay, so this parametric form, right, is denoted as p theta, where theta are the set of parameters that we would estimate. Now this p theta is what is referred to as a model. So we talk of large language models and diffusion models and so on, right? What is a model there? A model is the parametric assumption that we have made on the underlying unknown distribution that we are trying to estimate. Okay, so examples can be, so I talked about the examples of lines, etc., right? So mx, if you assume your model to be mx plus b, then this theta, or the set of parameters, will be m and b. So those are the set of parameters that we are trying to estimate, and this is a model that you are trying to estimate. So now we start by assuming, making a parametric functional assumption on the unknown distribution function that we are trying to estimate. Now typically these models can be, so these can be, these are, today all the models are neural networks. So we choose neural networks because they are universal function approximators. I assume that the students in this course know about constructing neural networks, and how to train them, etc. We will cover that in some of the initial tutorials that we would offer as a part of this course. But anyway, p theta or the parametric form that we make on that we assume on the unknown distribution function are the go-to choice today are neural networks. The transformers that are used in the state-of-the-art large language models are all specialized neural networks. One can use convolutional neural networks, or recurrent neural networks, or feed-forward neural networks, any kind of neural networks. Basically, I mean, there's nothing sacrosanct about neural networks other than the fact that they are universal function approximators, in that they can approximate any function to arbitrary closeness given enough number of parameters. But as far as the broad recipe is concerned, p theta can take any parametric form. Okay, the goodness of the underlying estimator depends on the parametric family of functions that you have assumed. People resort to neural networks because they have the universal approximation capability, which means that given enough parameters, they can estimate any function to arbitrary closeness. Okay, the first stage in the recipe towards solving the problem of Gen AI is to assume a parametric form on a known distribution function. The second thing that we would do is that define and measure a divergence metric between px and p theta. Now, see, whenever you are solving a problem of estimation, how do we do that? It's trial and error. So, what do you mean by trial and error? The most primitive form is trial and error, where suppose you make a model assumption, you would see whether the assumption that you have made about the model fits the data or fits the observation that you have made or not. Okay. Now, what do you mean by checking whether it fits or not? Is define a distance metric. Okay, see if you can measure how far is the model that you have assumed from the reality, which is px. Now one might ask a question, uh, when I do not even know what the underlying px is, how do I even compute this divergence metric, right? I mean, that's a valid question, and several algorithms answer that question in different ways. Different algorithms answer that in different ways, and we will see that in the course. But anyway, the first step is to define a divergence metric between px and p theta that would tell you. So let's call that d of px and p theta. This is how it is denoted in practice. Any divergence metric between distribution functions is denoted using this notation. There are double bars here. So this measures how far are px and p theta from each other. So suppose we had a divergence metric, okay, distance metric of sorts. We have the distance metric matrices such as the Euclidean distance, etc. That would tell you how far are a given pair of points are, how far are a given pair of lines are, and so on, right? We will define a similar divergence metric between the pairs of distribution functions. So if you imagine two distribution functions as points, the question that we are asking is, given two distribution functions, tell me how close or far they are using some metric. And imagine that we define a metric of that sort. I mean, the usual divergence metrics that we see are the Kullback-Leibler divergence or KL divergence, and the Jensen-Shannon divergence, F divergence, and so on. So we need a way to measure how far or close a pair of distribution functions are, where p theta is my model distribution and px is my real distribution that I don't know. So once I have this divergence metric and I know how to compute it, so readjust or not adjust the parameters theta of p theta such that the defined distance metric between the true distribution and the model distribution is minimized. That's it. So this is the optimization problem. So mathematically, you find the parameters theta such that it minimizes a divergence metric, okay, a distance metric between the true distribution and the model distribution. So this optimization is over the parameters of the model. So what is this notation? Argmin means that give me that theta that would minimize this particular function. Okay, that's what the notation is. So this process of finding the parameters of the model such that a distance between the true distribution and the model distribution is minimized is what is referred to as training the model. Okay, that's it. So if we are able to solve this optimization problem and find a theta star that would make this divergence metric as low as possible, then the model distribution p theta that my model is imposing has now become close to px, the underlying distribution. So which means that we have solved the problem that we started with. Okay, so this is the general recipe. So further in this course, what we will be doing is that we will be looking at ways of doing this. What model? The open questions are what choice that one do for p theta, and what should be the choice for the divergence metric that one should be looking at, and how do you solve this optimization problem, and more importantly, how do we compute this divergence metric when we do not have access to px. So see, we are begging the problem in a way, right? We had never had access to px. The very problem that we are trying to solve is that we don't have access to the underlying distribution. Now when we do not have access to the underlying distribution, while we only have samples given from it, how do we solve, how do we compute this divergence metric, and how do we even solve this optimization problem, are the questions that we will be answering. And every algorithm will give you different ways of doing it. Let's say the variational divergence minimization will give you a different way, diffusion models will tell you to do it in a different way, the autoregressive models will tell you to do it in a different way. The knobs that we will be tweaking and training will be of what choice of p theta that we will be making, what is the particular algorithm that we will be using to solve this optimization problem, and how do we compute the divergence metric when we are not having any knowledge about px and p theta. Okay, so those are the questions that we will be asking further in this course, and we will look at multiple ways of doing it. Let me just quickly recap the foundational problem of Gen AI before closing this class. So the problem that we will be solving in generative modeling is that we are given n realizations samples of which are the outcomes of a random experiment, and there is a random variable that is translating all of this into something that we measure, which are the members of a d-dimensional real space. The question that we'll be asking is, this is the data set given n data points, which is a data set with which are coming from an unknown underlying distribution function. What we would want to do, oh okay, I made a mistake, I wrote this as objection, this is not objection, this is an objective. Okay, the objective is to estimate the underlying distribution function and also learn to sample from it, because we are solving the problem of generative modeling, and in generative modeling sampling is a essential part. Now, what is the general framework to solve this problem is that we start by assuming a parametric form of the unknown distribution that we are trying to estimate, denote it with p theta, where theta are the parameters, and typically these are neural networks in today's world, and you define and measure a divergence metric between the true distribution and the model distribution, which will tell you how far or close these pair of distributions are, and then learn the model, right, or rather estimate the parameters of this model p theta such that this divergence metric between these two is minimized. Okay, there's actually a fourth or 3b sort of step where, so once px is measured, use it to sample. So remember our problem, one major part of our problem was to learn to sample from the underlying distribution. So now how do we do that? Once we get the underlying distribution measured or estimated, you can say estimated, that's a better term. Once we have the underlying distribution estimated, so we would use it to sample from that distribution. Multiple algorithms do it in different ways, and we will see how to do it in the due course of this particular course that we are looking at. We will look at several ways of how to choose p theta, how to solve the optimization problem, how to measure the divergence metric, and so on. Okay, so with that we will conclude this particular session, and we will go with the variational divergence minimization algorithms in the coming lectures. I urge all students to go back and refresh your probability theory fundamentals. Some of it is covered in our tutorials, so please go through them carefully. This is only an overview, philosophical, mathematical sense of overview of what is happening. But I would assume that all students that are coming to this course are rigorously trained in probability theory. Otherwise, the course will sort of the students will not be able to appreciate the content of the course well. Okay, so see you in the next class. Thank you, everyone.